models that we started out with today, and I'll show you how to use those using the scikit-learn libraries, but this time in the specifically for materials applications. Before we go to the applications of these models, I'll go through some of the basic things once again, little slower this time, and so that you follow what I'm doing. I'll show you the script, and then I'll also show you how each of these things, what they do to your data, to your model training. Okay, so this the models that I will discuss today are firstly the linear regression model, which is the absolutely simplest model you can train. Kind of obvious, but there is a lot to learn from that model itself. And one variant of that, which is called lasso. I'll come to that. Probably both in terms of conceptually and historically, ridge regression preceded lasso. But whatever, I have prepared it for lasso today, and maybe I'll discuss ridge regression in the next lecture. And I'll also compare the two, what lasso does and what ridge regression does, and so on. Okay, but before you train any model on any kind of data, what is important is to do data pre-processing, which is very important. And this has been discussed in detail by Dr. Misha. I will just I will go through some of the standard preprocessors that one uses and which works in which case a bit more slowly and systematically. So the reason we need to do data pre-processing is that different features can have very different scales. And today, this you have heard a lot about this possibility about this, how it can create problems in model training, because if one feature has values that are very large compared to a second feature, as far as the outcome is concerned, it will be dominated by the feature which has large values. So I'll show you in the concrete material context some examples so that you appreciate it better. So here is the data set that we had created. I had shown you in one of the earlier classes. This is the heat of formation data set for ABAC3 kind of materials, and the features that are calculated here are the eigenvalues of the sign matrix. So, oops, I'm sorry. So we set the maximum number of atoms in the unit cell to be 30. So here we have, maybe I should make it a bit bigger. Let me just give me a minute. I'll make it a bit bigger so that you can read it clearly. Yeah, so at least you should be able to read that sign matrix eigenvalue 30. So all right, so you see these values, these are several thousand, tens of thousands. Those are the kind of values that you see here. Can I make it a bit bigger? Yeah. So from few thousand to few tens of thousands are the non-zero eigenvalues. That some are of course zero, but the non-zero ones can be from hundreds to hundreds, tens of thousands. Whereas let us look at another feature for the same set of materials, and this time we have calculated ACSF. This also I had shown you. Just taking a while. Basically, the point is I'll show you once it opens. Firstly, it's a very sparse feature. Most of the entries are zero, but let me zoom into some parts that are non-zero. See, these values are like 2 and 1 and like that. So that is the whole point. So there are some features which are very small values, small dispersions, features that have large values, large dispersions, and unless you do something, the training will be dominated by features that have large values. So therefore, what you have to do is scale them somehow, and there are different ways you can uh, do scaling or transform them, not just simple scaling. So a few of these are discussed, or maybe all the standard ones are discussed in or implemented in scikit-learn. So I'll go through them one by one. So one is the standard scalar, which is the first one. So what it does is from the given data, from the given features, it just removes the mean. So x, the feature, is transformed to a new feature x primed. uh, First you subtract its mean and then divide by the standard deviation of x. And so the new variable or the new feature that you get x prime, by definition, by construction, has mean equal to 0 and standard deviation equal to 1. Then the other commonly used preprocessor or transformer is the min-max scalar, where you can transform your data to a set where it is scaled between, you can decide to scale it between 0 and 1, or you can scale it between, some in some range u to l. And if you just use this relation, then it will be scaled between 0 and 1. Or if u to l is your intended range, then you can do a further transformation. So the variable x primed is now between u and l. Uh, Robust scalar is another scalar. It takes care of outliers. Outliers are values for which the y's are very different from what you have from the predictions. So if you have outliers, then what robust scalar does is, firstly, it removes the median and not the mean of the feature, and then it scales between the first and the third quantiles. That is the number that is at 25% and 75% of the distribution. So this takes care of the outliers. See, in standard scalar or mean max scalar, if you have one value of the feature that is very different from all the others, very small or very large, then that can dominate the mean, the standard deviation. But if you are removing the median and then scaling it between the quantiles, then these numbers are not very much affected by one value, which is, or few values which are very large. So this is a better way of taking care of outliers compared to standard scalar or mean max scalar. And the other slightly more sophisticated way of taking care of outliers or transforming your data to any intended distribution is what is called the quantile transformer. So one often convenient transformation is that you take a feature and transform it to a Gaussian distribution with, say, mean 0. So one way of doing it is, so the quantile transform takes the feature to some desired distribution G, which could be your Gaussian distribution, need not be, it could be uniform distribution also. But how does it do it? It is based on this relation. So G inverse f of x. So now we have to understand these quantities. If you want, you can, I will not go into all the detailed mathematical discussions here, but if I'm just giving you the overall idea, if you are interested, you can go ahead and read up further details. So so first we have to define what is a quantile function. There's something called a quantile function. So quantile function of a probability distribution is the inverse of its cumulative distribution function. So suppose D here, this curly D is some probability distribution function, our usual probability distribution function. It can be anything. And then the probability that the random variable has a value which is less than some number x in its range is, of course, this integral. So the probability density d integrated from minus infinity up to x, or whatever the range of capital X is. From the lower end up to x, you integrate it. So that by definition is the cumulative distribution function, okay? Capital F, which is a function of small x, that is the upper limit of that integration. And you note that if, of course, D is properly normalized, then f of x is also a probability, and it lies between 0 and 1. Now, the quantile, for once you have defined or you have understood this cumulative distribution function, capital F, the quantile distribution or the quantile function of the distribution function D is defined by this. So QP given a value P is F inverse P, so which is defined in the following way. So it's that value of x, or it's the infimum of the values x for which f of x is greater than p for a given p. Okay, so you can just think a bit about it. But the point here is that once you know this f, which is the cumulative distribution of probability, cumulative what do you call it, cumulative distribution function of a probability distribution D. So the G inverse is the quantile function of G. So I have an intended distribution G. I have its quantile function G inverse of the distribution function F. So I calculate F of x, do inverse G inverse of that, and that will be distributed according to G. So that is the idea. So if my target distribution is Gaussian, I'll do accordingly. So G would be my Gaussian function, and I would be using G inverse, which corresponds to the Gaussian distribution. Okay, so now I will like to show you what each of these transformations do to a given data. Okay, so let me go to processing data. Just a minute. Yeah, so let me increase this a bit. So here is the original data, and two features are shown here. So x-axis is one feature, y-axis is another feature. Oops, lost it, just a minute. Yeah, x-axis is one feature, y-axis is another feature, and on the left you have the full data, and what the right side shows is some of the marginal outliers have been removed from the data. So you see most of the data is in this region, and there are some outliers. So once those are removed, this is the distribution of data that you have, and the range of the first feature is like between maybe 0 and 10, and the second one along this axis is between 0 and 6. Okay, now what does a standard scalar do? This is what a standard scalar does. So focus on the right panel without the marginal outliers. And so what has been done is the mean has been removed and it has been scaled by standard deviation. And the first feature now ranges between -2 and 3 or 4 maybe. And the second one here is between minus zero point 0.2 and plus zero point 0.2 or something like that. So yes, of course, the scale has changed, but the values are different for the two features. Then there is something I did not probably. So there is this min max scalar. So what this does is I probably did not discuss this. But what this does is it scales the first one between 0 and 0.7 or 0.8, and you see the scale of the second one, which is very, very different. So this, so they are trying. So one is attempting to scale data so that all the features are in the range 0 to 1. However, it doesn't always scale necessarily between 0 and 1. Okay, so as as you see, the second feature values are largely between 0 and 0.005 or something like that. So it doesn't really help. Max app scalar is closely closely related to min max scalar. So I will skip that. So robust scalar, you see, so this is where you remove the median and then scale between the first quantile and the third quantile. Here you see the ranges are similar. Okay, you see here it goes from maybe -1 or maybe a bit more, -1.5 to 3, and same thing here, very similar ranges. So this is what we were saying, that this transformer, this processing helps you handle outliers better. And I did not discuss the power transformer, but quantile transformer. So here, as I said, you can use quantile transformer to transform it to any desired probability distribution. So I think these two show you quantile transformation. Uh, I think this gives you a uniform, yeah. So these two are uniform distributions obtained from what the quantile transformer. And you see you have 0 to 1, 0 to 1, very uniform distribution of your feature values. And quantile transformer here gives you a Gaussian distribution, which is like this. So the range is somewhere between -3 or -4 to 4 or -4 to 3, but both the features look very similar in terms of their distribution. So, so what you have to sort of carry from here is you have to kind of understand what your feature is, what sort of distribution it has, what are the values it has, and then if there are outliers, then you have to be careful about which transformer you use. The quantile or this robust scalar work better when you have outliers. Okay, so with that, I will go to the discussion of linear model. Let me go to the code and then see what are the things that we have to import. Yeah, so there is something called, let me use that. Yeah, so here, these are matplotlib, seaborn, numpy, etc. Now here is the main part. I may have repetitions here, but nevertheless, so what I'm importing from scikit-learn is the linear model. If you are doing linear regression, I mean, once I have imported linear model, this line is probably not required, but I'm in the second line, I'm specifically importing linear regression. Third line, I'm importing from SciPy stats Pearson correlation function. And then the fourth line imports matrix that will be used to measure the performance of the model. So mean squared error, mean absolute error, R2 score, explained variance, these things. And cross validation research CV, these are not required for linear models, so this was in some other context. And I also, in the last line in this highlighted block, I import pre-processing, and I'll do some pre-processing before I train the model. And for pre-processing, specifically, see, you can either have this line or you can have this line where you specifically import certain pre-processing. Uh, but for some reason, I had written both. So it doesn't matter. Okay, then usual pandas, etc. So what I have is what I showed you is this data file. Okay, saved as a CSV, which is the data set for heat of formation for the ABAC3 class of materials that we had downloaded, and I had shown you how to create this data set using describe. So what I have there are the eigenvalues of the sign matrix and the heat of formation values. So these are being read in as a pandas data frame. Okay? So HOF data is a pandas data frame which is being read from that .csv file. Okay, so these are just lines that will tell me what is the shape of that data frame and how many samples do I have, what is the size of the data set. Okay, then what we do is we shuffle the data randomly, we shuffle the rows. So axis equal to 0 means it is being shuffled uh, row wise. So the rows are shuffled up and down, and yeah, so all the, I mean, the complete data frame is being shuffled. So that is what frac equal to 1 means. uh, I have already, or I can maybe show you this thing. So what I have done here is that the 10th eigenvalue of the sign matrix. So in this line, the 10th eigenvalue of the sign matrix is being read in from the data frame. And I'm printing the percentiles, the 0, the 25, the halfway mark, 75 and 100. Etc. So you get a feel of the distribution of this particular feature. You can do it for all features. This is just to show that how you can get a feel of how your features are distributed, what kind of pre-processing you might want to do. Okay, then you have to set your target. So the target value on which you will train your model is here stored as y, which is the which is the column of the data frame with the header PPE eta formation. Okay, so that sets y as so this is the column, the last column we had in the CSV file with the heat of formation values. And here what I'm doing is, just to show you, I'm plotting the distribution of this 10th eigenvalue before any pre-processing has been done. So we'll see it when I run this script. And this is just for our, again, understanding. This will plot the distribution of the heat of formation values. Now, if I can go back to that, so this is the data set that we had. Yeah, so the first column you see is with the header materials. These are material names. So these are just for our understanding, and we don't need it for any model training. And the last column is the target variable, in this case PPE heat of formation. So what we do in this line is that we drop these two columns. Okay, the material, we don't need it for model training. And the heat of formation values, we have to remove those because those are not features. Those are my target values. So I cannot have them. So whatever remains are now this, the features, the X matrix. Okay. So now here X, which was a pandas data frame, is transformed to a NumPy array. And here the test train split is done. So we split both X and Y into training and test set. And test size is 0.3. That is 30% of the data is kept as test data and 70% is used as training data. So this is just again to see what is the shape of that. Now here comes the transformer. The data pre-processing. So what we do is quantile transformation, and the output distribution is normal. So this is what I was telling you. You can use quantile transformer to transform your features to any distribution you want. In this case, we are transforming it to a normal distribution. And so this is according to my features, the training features, X train. So the transformation is done according to the features in the training set. So this defines the transformer. Okay, so using this data, the transformer will be found out. And once the transformer X scalar is found, we have to transform the training data and then the test data. And these are the sort of syntax using which you transform your data. So X train is transformed to X train scaled, and X test is transformed to X test scaled. And here the 10th eigenvalue is scaled. I could have found out from the scaled X trained also, but I apply the scalar here and look at what is the scaled version of the or transformed version of the 10th eigenvalue. So we'll see this just to understand the difference what scaling does. And then we'll see its distribution in this plot here. So what we have done so far is that we have taken the data, we have read it in as a pandas data frame, then we have looked at some distributions, then we have dropped two columns. One was just a header or the sort of materials name column, the other is the target variable column. The remaining part is my feature matrix. I have defined the transformer for data pre-processing on this feature vectors, and then I have split my data into training part and test part, and then found out the transformer based on the training part. I have done the same transformation on the training set and the test set. Okay, and then we will also look at how one particular feature has transformed under this transformation for our understanding. Okay, then we scale the y, then we define a scalar for the target variable y. Okay, and we scale the target variable also. So far it's data, reading in data, data pre-processing, understanding your data. And finally here we get to creating the linear regression. So this part just creates the linear regression. So the first line here, linear model, linear regression. And it is fit using X-trained scaled, so the scaled training features and the scaled target values. And after the training, we will write out the regression coefficients and the regression intercept. So let us recall, what do I, let me get to my, so remember this is the linear regression model. Y is written as a function, linear function of the feature vectors. There are p of those. And the task is to minimize the set of W's so that this square of the residuals between the predictions given by xw and the true values y's, the square of the deviations, sum of the squares of the deviations is minimum. Okay, so and these w's are the coefficients and w naught is the intercept. So let us run this. It will stop here and see what we get. Okay, it's running here. Yeah, so what you see here on the screen is the 10th eigenvalue before any pre-processing. Most of the values are 0, and then you have a few which are which are large. Some are somewhere between 500 and 1000, and some are around 2000 or above 2000. And this is the distribution of the heat of formation. Uh, these numbers vary between -2 and 1.5. And this is the distribution of the 10th eigenvalue after the pre-processing. So you still have a peak so first of all, you see that the range has changed. Okay, now it is somewhere between maybe -5.5 to 2.5, and whereas there is still a peak at the lowest values, but the rest of it is more uniformly distributed. Maybe it was a very skewed distribution to start with. So it's not exactly normal, but apart from that peak at the very small values, the rest are somewhat like, peaked in the middle. Okay, but the range has definitely changed significantly. And then these are the coefficients. So there were 30 eigenvalues, so 30 features. So you have W1 to 30 here, and the line after this shows the intercept, the W0. And what I would like to point out is that you see most of the W's are large in the sense that none of them was very close to zero. Some are like 0.04, 0.09, but not very small. Okay, so all right. So now what we'll do is we'll go ahead and see what we do with this. So so far we have just done the model training and we haven't really predicted anything. We just stopped there. So this line, once you have trained the model here, this line, the highlighted one, predicts the y value. So this y value is predicted based on the scaled features of the test set. So there is this function. Your model is regression reg. So reg dot predict. This will predict, given your test features, it will predict the target values. So once you have made the predictions, you can calculate various metrics that measure the performance of the model. So R2 score, I'll show you once again just to remind you. Then Pearson correlation between the predicted value and the actual true value. Then you can calculate the explained variance. Then you can calculate root mean squared error, and you can calculate the mean absolute error. So let us look at these quantities, expressions for these quantities. R2 score is this, where the y hats are the predicted values and y bar is the average. So basically this is a measure of how your model is doing compared to the situation where all the predictions were just y bar. Okay, and these values can be, for a good model, the value is close to 1, and it can go to negative also. If your model is very bad, it can go to negative values as well. The explained variance is slightly different in sense, but very closely related to the R2 score. So you see, it's the ratio of 1 minus ratio of the variance of y minus y hat by the and the variance of y. Pearson correlation coefficient is just usual definition in statistics. Mean absolute error is the average of the absolute deviation between the predicted and the true values, and root mean squared. The mean squared error or the root mean squared error. Here it's the root mean squared error. So you take the mean of the squared errors and take a square root of that. So in principle, you can calculate all of these quantities and see how your model works. So basically, you want mean absolute error or mean squared error or root mean squared error to be as small as possible, close to 0, whereas R2 scored or explained variance or Pearson correlation coefficient should be close to 1. So how does our model do? Let us so before I show you how the model does, let me alert you that what we have done here, the predictions that we have done here, the matrix that we have calculated here are all on the scale data. But when you are doing a physics problem, when you are doing a materials problem, you would like to quote your errors in the actual physical units. Sorry. So you would like to do it, you would like to have your errors, in particular, you would like to have your mean squared error or mean absolute error in physical units. So therefore, it is important to transform it back to the original distribution. Okay. So just as you can define a data distribution, you can define an inverse transformation. Just as you can define a data transformation, you can define its inverse transformation. So all you have to do is, you had a y scalar. Uh, you just have to say y scalar inverse transform. So then it will take the scale data and take it back to the original distribution. And so same thing here. Yeah. So yeah, that's all I need, because if I want to calculate the test set errors in the original data, so I just need to inverse transform the y data, the predicted y, and the test y, actual test y I already have. So okay, so the predictions are inverse transformed, and then I recalculate the MAE, the RMSE, and the R2 score, etc. All right. So let us now run the full thing and see what we get. So I just out. I've seen these things. Okay, relative error in Y. And this is what you typically do in any regression task. This is for the training set data, the true heater formation and the predicted heater formation. In the ideal case, you expect a straight line. Okay, they should match exactly. So x equal to y or y equal to x straight line. This is very far from that. Not surprising. And this is the same plot for the training data. I'm sorry, the test data. Did I have that? Or I did not have the distribution. Oh, I already showed you the distribution for the eigenvalue. And here are some of the numbers. Okay, so results for the original data, if you can read this. So these are the mean absolute error for the training set and the test set after inverse transformation. So these are in actual physical units. So what I have here is the prediction error for heater formation is 321 MeV per atom. The units were EV per atom. So this is 321 MeV per atom. So that is my test set error after I have done the inverse transformation in a linear model. And the R2 score is 0.21, which is considered quite bad. Okay. Even when we go to, I hope I'll be able to show you by the end of this week, when we go to something like a random forest model, this should improve significantly. Okay, I have not discussed the rest, so I'm not discussing what is mean of the relative error on Y, but these are some of the more important things that I wanted to show you. So the apart from how to sort of construct the regressor and then train your model and make predictions, etc., for which I will share this. The important point I want to convey is that the R2 score is pretty low for a linear model, and it's not surprising. It's very, very unlikely that the heat of formation would have a linear relation with the eigenvalues of the sign matrix. So quickly, in the next few minutes, I will show you. Oops. This was linear. Yeah, the next model I wanted to show you today is lasso. Okay. And yeah, lasso is one of those shrinkage methods. You know what a linear regressor does is it tries to use all the features to fit a model, and whereas shrinkage methods puts a penalty on these coefficients w. And as I said, ridge regression was probably I should have discussed it first, but I'll do it next time. Today I start this discussion. If we cannot finish this, I'll discuss. I'll continue next time. So here, what it does is it puts a penalty. So it tries to sort of regularize these coefficients. And in fact, what happens in this lasso, which is called the least absolute shrinkage and selection operator, is that some of these coefficients can turn out to be exactly zero. So one thing it does is that it uh, reduces the size of your feature space. At the same time, it helps you in feature selection. It tells you that some of the features could be not at all important in making the particular in predicting the particular quantity you are interested in. So here, how is it different from the standard usual linear regression? In the linear regression, you are just trying to minimize this squared deviation part, this first term here. Here you have this second term, but note that at least the way it has been implemented in scikit-learn. So you have this factor of 1 over 2n, where n is the number of training samples. So this plus this. And alpha is a hyperparameter of this model. So you train your model for a specific value of alpha. And of course, as alpha changes, your model performance will change. So what value of alpha should you take? This is a standard question for any model which has hyperparameters. Lasso or ridge regression, these are particularly simple models which have just one hyperparameter each. But when we go to a random forest, we'll see that there can be many hyperparameters, and you have to systematically optimize those. So you have to use the best set of hyperparameters for your model before you do the full model training. Here, the hyperparameter space is one-dimensional, so it's fairly simple. I'll just quickly go over the idea of cross-validation, which we have discussed earlier. I'll just go through it once more. So what you basically do is, the example here is given in terms of a 5-fold cross-validation. So what you do is, first of all, you have your full data set. You split it into training data and test data. And suppose I'm now working with the training data and I divide it approximately into 5 folds. Now, for each value of alpha, first I have to choose a range of alpha. And in this range, what are the specific values of alpha that I use? Now, for each of those alphas, what you do is, in turn, you train your model using 4 of those folds, data in 4 of those folds. So when you are here, you train your model using fold 2, fold 3, fold 4, and fold 5. So that's your training set. And then you test it or validate it on the data in fold 1. So you get a, say, mean squared error. You do the same task, but now you hold out fold 2, you train it with fold 1, fold 3, fold 4, fold 5, and you fold 2 is your validation set. You get another mean squared error, and so on. And you will have 5 such cases. So the overall cross validation score is average of these mean squared errors. So for k folds or k fold cross validation, this will be an average of k numbers. And in this case, k is equal to 5. So you do this for each alpha, and the alpha that gives you the minimum cross validation score is your optimum value of alpha. That's the general idea of cross validation. Here in Lasso, you can choose your own range of alpha. If you don't, scikit-learn has its own logic of choosing a range of alpha and doing this cross validation. So that is the only thing that is differing here in this Lasso routine as compared to the straightforward linear regressor that we used. So uh, we import all the necessary libraries from scikit-learn, etc., etc. I'll just show you. So I have, because I have imported the linear model, Lasso is sort of part of that. So I'll show you just that part. The scaling, the split, everything goes as usual. Yeah, the model is defined here. And in this example, I have put in a specific value of alpha. Okay. So here I'm not trying to optimize alpha. I just put in my value of alpha and do the whole thing just as before. So the fitting is, so it is now fitting a regression model with a lasso model with alpha equal to 0.01. So we can just go ahead and run it. It's the same data set. Yeah. So we stop. I'll show you the maybe the actual results next time. But what I want to highlight here is that you see these are the coefficients, and what you see is that many of the coefficients turn out to be exactly 0. So that's what Lasso does. And so many coefficients are 0 for alpha equal to 0.01. Now that may not be the optimal value of alpha, and we will try to find the optimal value of alpha next time. And the intercept, next slide gives you the intercept. So we saw how to use the linear model and then Lasso for a specific value of alpha. And what we see is that Lasso can put many of the coefficients to 0. So, you can go ahead back and maybe train some other model, maybe a linear model, removing these features for which you got coefficients to be 0. How to choose the optimal value of alpha, that we'll see next time. Ridge regression we'll see next time, and we'll try to understand the different subtle differences between the ridge regression and the lasso models. And then next time we'll move on to maybe the random forest model. Okay, so I think I'll stop here today. If you have questions, you can ask or type in. I'll wait for 2 minutes, maybe a minute. See, again, let me tell you that what I'm showing is a very, very simple exercise. Just shows you step by step how to call routines from scikit-learn, how to call libraries from scikit-learn, use those. You just refer back to that their user guide, scikit-learn website. Once you follow one method, it is very simple to follow the other methods. So, you should spend some time doing these simple exercises, and so that will give you more confidence and understanding. All right, so we'll meet on Wednesday. Shivankar, would you like to add anything? Yeah. All right then. We'll see you on Wednesday.